from Peking University. Our paper is about gradient boosting decision tree to higher dimensions. It is joint work with CTI Zurich and Tencent in Croatia. So first, I will talk about the background. Gradient boosting decision tree, GPT for short, is an ensemble machine learning model widely used in academia, industry, and data science platforms such as Kaggle. GPT uses the boosting strategy that trains a set of regression trees to improve performance. When predicting the training data, GPT sums the prediction of all trees. For example, the prediction of this man is the output of the first tree 5 plus the second tree 5. The training method of GPT starts from the root tree node and greatly splits tree nodes with a top-down manner. The coordinate structure is called the gradient histogram. The x-axis is the feature value, the y-axis is the gradient sum of training data fall into a value range. The training procedure of GPT contains 3 main steps. First, we read all the training data and propose several candidate splits for each feature. The mainstream method is called quantile sketch. Second, build gradient histogram. Based on the candidate splits, we build gradient histogram. Basically, we put first order and second order gradients into the corresponding histogram buckets. Third, tree splitting. We scan the histogram from left to right and find the best split, giving the maximum loss gain according to the formula. So the size of a gradient histogram is 2 multiplied by the number of features and the number of splits. We found that the performance of existing distributed GPT systems decreased with high-dimensional datasets. So we ask the question, what are reasons behind the bottlenecks of existing systems for high-dimensional data, and how can we fix it? We found that the reasons are twofold. First, in histogram construction, the traditional method needs the values of all features, so high dimensionality leads to more computation cost. In tree splitting, distributed GPT needs to merge local gradient histograms on workers. Since the size of gradient histogram is proportional to the data dimensionality, higher dimensionality leads to more communication cost. So how to solve the challenges in histogram construction and tree splitting? In histogram construction, the challenge is high computation cost. With this scenario, the first question is how to build one single gradient histogram. Considering that high-dimensional datasets are generally sparse, we propose a sparsely well method that only access the non-zero features instead of all features, so we can reduce the computation cost. After building one single histogram, let's study how to build gradient histogram in parallel. Think about tree structure. As the tree goes deeper, we have more tree nodes, and tree nodes in one layer can be processed in parallel. We design a load-to-instance index. Each tree node has a range in the index, so we can directly find the training data on that tree node. We further study how to build one gradient histogram in parallel. The motivation is that the first few tree nodes in a tree have many instances. For example, the root tree nodes has all the training data. To address this problem, we propose a parallel batch training method. Since each tree node has a range in the load-to-instance index, we divide the range into batches and process mini batches in parallel. After histogram construction, the last operation is tree splitting, and the challenge is high communication cost. First, how to merge local histograms on workers. This involves the underlying system architecture such as MapReduce, ORReduce, and parent server. We chose parent server since it has been proven to be efficient for high-dimensional cases. Then how to transfer histograms through the network. Transferring the original histogram can be very expensive. We choose to compress the histogram with quantization. So basically, we transform each floating point type item in the histogram to 1 byte in binary representation. After merging the histogram, the last decision is how to assign splitting tasks to workers. As tree nodes in one layer can be processed simultaneously, we design a task scheduler that uses a round-robin strategy to assign all tasks among all the workers. And when receiving a splitting task, one worker needs to find the best split from the grading histogram. The grading histogram is partitioned over several servers, and putting the entire grading histogram is expensive. To address this problem, we propose a two-phase split approach. In the server phase, the server finds a local candidate from the histogram partition, including the feature index, the feature value, and the loss gain, and send it to the worker. In the worker phase, the worker chooses the best one from all the candidates. Here's the system overview of DemBoost. We have servers, workers, and the training datasets. I will show how DemBoost works. We partition the dataset to workers, build a histogram with multi-threads, and send histogram to servers after compression. The scheduler assigns tasks to workers. Each worker uses the two-phase tree splitting to find the split row of tree nodes, with which we update the tree structure and the load-to instance index. The index will be used in the last iteration of histogram construction. Let's use our experiments. We use 3 datasets to compare managed DemBoost with MLlib, XGBoost, and LightGBM. RCV1 is a public dataset. Synthesis is an artificial dataset, and gender is a real dataset from Tencent with up to 1/3 million features. We use 2 clusters. Class 1 has 10 machines. Class 2 has 50 machines. On the general dataset and class 2, we gradually add our tag list and show the performance change. As the results show, our proposed method can significantly improve performance. We can build 1 tree within 40 seconds. Then we'll show the end-to-end performance of 4 systems. On all 3 datasets, our system DemBoost achieved the best performance. It is up to 9 times faster than the baselines. And we also find that the histogram compression does not harm the model accuracy. To conclude our work, we study distributability in this work. In histogram construction and tree splitting, we propose a series of tag lists. By combining these tag lists, we implement DemBoost, a distributability system, and achieve up to 9 times improvement. So thanks. Any questions?
Thanks for your talk. Okay. So I have one question. Okay. Have you compared with a single machine multi-threading setting?
Yeah, so in our paper on a small data set, we compare the single node implementation, and we find that our system still outperform the state of the art.
Yeah. How many times outperform?
Single is not so large compared with the distributed experiments. It's about 2 times improvements.
Great, thank you.
Okay, thank you.